Okay, we're continuing with section 6.2, non-uniform circular motion. So let's look at the figure. And when a particle moves with varying speed in a circular path, its acceleration has radial and tangential components. Therefore, the force must also have tangential and radial components. So the total acceleration is equal to the radial acceleration plus the tangential acceleration. Therefore, the total force, the total force exerted on the particle is the sum of the radial force directed toward the center of the circle, and that's responsible for centripetal acceleration, and the force in the tangent to the circle, which is responsible for the tangential acceleration that represents the change in the particle's speed with time. The speed could be increasing or decreasing. So let's take a little quiz. A bead slides at constant speed along a curved wire lying on a horizontal surface as shown in the figure. Draw the vectors representing the force exerted by the wire on the bead at points A, B, and C. Now, because the speed is constant, the only direction the force can have is that of the centripetal acceleration. The force is larger at C than at A because the radius at C is smaller. There is no force at B because the wire is straight. So why is the force larger at C? Well, if you recall, the centripetal acceleration is equal to v squared r. If r goes down, the acceleration goes up. If the radius in the denominator goes down, the acceleration goes up. Well, we put that into the force equals mass times acceleration. If the acceleration goes up, the force goes up. So if the radius goes down, the force goes up. All right, let's look at bead slides at constant speed along a curved wire lying on a horizontal surface as shown in the figure. But suppose the bead speeds up with constant tangential acceleration as it moves toward the right. Now draw the vectors representing the force on the bead at points A, B, and C. So in addition to the forces in the centripetal direction in part A, there are now tangential forces to provide the tangential acceleration. So you can see the radial components and the tangential components at both A and C, but at B, it's only the tangential force. There is no radial force because there is no radius. All right, let's do an example. A small sphere of mass m is attached to the end of a cord of length r and set into motion in a vertical circle about a fixed point O as illustrated in the figure. Determine the tangential acceleration of the sphere and the tension in the cord at any instant when the speed of the sphere is v and the cord makes an angle theta with the vertical. All right, let's conceptualize this. Compare the motion of the sphere with that of the child on the Ferris wheel. Both objects travel in a circular path. Unlike the child, however, the speed of the sphere is not uniform in this example because at most points along this path, a tangential component of acceleration arises from the gravitational force exerted on the sphere. So we can categorize this as follows. We model the sphere as a particle under a net force and moving in a circular path, but it is not a particle in uniform circular motion. We need to use the techniques discussed in this section on non-uniform circular motion. So if we analyze this from the force diagram, we see that the only forces acting on the sphere are the gravitational force, which is mg, exerted by the Earth, and the force T exerted by the cord. We resolve Fg, the gravitational force, into tangential component mg sine theta and radial component mg cosine theta. From the particle under a net force model, apply Newton's second law to the sphere in the tangential direction. Okay, the tangential force, the sum of the tangential forces is equal to mg sine theta, and that's equal to mass times the tangential acceleration. Well, if you solve for the tangential acceleration, you get AT equals g sine theta. The ends cancel out. Now, let's apply Newton's second law to the forces acting on the sphere in the radial direction, noting that both the tension and the radial acceleration are directed toward the origin. We can use the equation for the instantaneous centripetal acceleration of a particle even when it moves in non-uniform circular motion. So the tension, the forces in the radial direction are the tension and mg cosine theta. And that's equal to mv squared over r, which you should recognize by now as ma mass times the radial acceleration, the centripetal acceleration. So the tension is equal to mg v squared over rg plus cosine theta. Now, let's think about this. If the theta is 0, which would be at the bottom of the figure, if theta is 0, then cosine theta equals 1. If it's at the top of the circle there, you've got the cosine of 180. What is the cosine of 180? It's minus 1. So we get the following. The t at the top is equal to mg v squared over rg minus 1. If it's at the bottom, it's mg v squared over rg plus 1. The plus 1 coming from the cosine of 0 degrees and the minus 1 coming from the cosine of 180 degrees. Note that the force T in this example changes direction because it must always point inward toward the string. Also note that V in the expressions above varies for different positions of the sphere as indicated by the subscripts. Now, at what speed would the sphere have, if it passes over the top of the circle if the tension in the cord goes to 0 instantaneously at this point? Let's go back at this. T at the top equals mg v top squared divided by rg minus 1. So let's set that that tension equal to 0. We get mg v squared over rg minus 1 equal to 0. Well, the mg, we divide both sides by mg. 0 divided by mg is 0, so we get v squared top divided by rg minus 1 equals 0. Well, let's add 1 to each side. You get v top divided by rg equals 1. Multiply both sides by rg, v squared equals rg, and then you take the square root, and v top is equal to the square root of rg or gr. And so that's the expression for the velocity at the top. It's the square root of the gravitational acceleration times the radius. Okay, but what if the sphere is set in motion such that the speed at the top is less than this value? If it's less than the square root of g times r. Well, in this case, the sphere never reaches the top of the circle. At some point on the way up, the tension in the string goes to 0, and the sphere becomes a projectile. So it follows a segment of a parabolic path with its peak below the topmost position of the spheres shown in the figure, rejoining the circular path on the other side when the tension becomes non-zero again. So the ball enters free fall for part of its motion near the top, and the string becomes slack during that time. Okay, this ends our discussion of section 6.2. Next, we will discuss section 6.3, motion in accelerated frames.